Hi, everybody, and welcome back to the AP Physics 2 live stream. Today, we're finishing off our review of thermodynamics, putting the finishing touches on it, looking again at PV diagrams, and finishing up with the concept of entropy. So technically, this is topic 2.7, internal energy and energy transfer. But moreover, we are talking about everything in thermo. As always, we'll begin with a quick lesson overview and talk over what we're going to be doing in today's 45-minute lesson. Then we'll do our daily warm-up. We'll pick up where we left off last class with a test question for you to solve. We'll do a warm-up, get your brains moving and thinking about thermo, and then we'll discuss what you need to know about entropy. We'll work through some guided practice, and in today's guided practice, we included more stuff about PV diagrams. Some feedback from my students said, we really need to spend more time on that, so we're doing it. Then we'll walk through a debrief and summary, and make sure that you know what the key takeaways were from today. Finally, we'll leave you with some AP exam practice, and I want to pre-apologize here. There are 2 free response questions in the AP exam practice because thermodynamics is such a broad topic with so many applications. We tried to select problems from the question bank that we thought might be reflective of the kind of stuff you would see on May 13th. So I am Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
I'm Brendan Eaton from Reedy High School in Frisco, Texas. Let's go ahead and take a look at the course overview for the rest of our review sessions. We are right here where you see the blue arrow, right at the end of thermodynamics, meaning that we are starting electrostatics very, very soon. So this is all in an effort to prepare you for this year's AP exam. So make sure that you've taken some time to figure out which one of those topics you really want to focus on. All right, and as far as today's lesson is concerned, we're going to start talking with gases and work, specifically PV diagrams again. And like Mr. Mancino said, my students say the same thing as well. They need more time on PV diagrams to really internalize what's happening on those diagrams. Changes in internal energy, we'll talk about how internal energy is changing. We'll speak again about work done by and on gases and help you just one further step in figuring out when work is done by the gas or on the gas, so on and so forth. We'll talk again about state changes and processes, and we'll also deal with mixing gases today.
And then we'll introduce the idea of entropy, one last state variable. We'll talk about reversible and irreversible processes, macroscopic versus microscopic changes.
You should already know how to determine work from a PV diagram. That was from yesterday's lesson. You should know the 4 types of processes, and you should know how to work with the first law of thermodynamics. Delta U is Q plus W.
So that by the end of this lesson, you can determine whether and how entropy changes. You can identify the direction of energy flow when discussing thermal equilibrium.
And the skills that we'll address today are explaining phenomena based on evidence produced through scientific practices.
Big day. So we're going to start with a warm-up where we left off yesterday, a cylindrical container with a frictionless piston initially locked in place, inside of which there is a fixed amount of ideal gas that is initially at room temperature and 1 atm of pressure. The cylinder is placed in a hot water bath. So the whole thing is just dunked. And you had to sketch a graph of pressure versus temperature. Well, right in the prompt, you can see that the piston is locked in place. It can't move. That means the volume is constant. If the volume is constant, increasing the temperature of the gas makes the particles of that gas move faster. And that means they collide and transfer, their momentum changes even more. So pressure is a measure of how rapidly the momentum of the particles in the gas is changing. or how hard they're hitting the side of the container. If they're going faster and faster and faster, they have more and more pressure. So it's the reverse of a graph that we saw 2 lessons ago. As temperature goes up, pressure goes up. So if people were actually doing this lab and they took a bunch of samples of pressure and temperature, that's what they would see. But you probably sketched a graph like that, just a nice linear relationship, spot on. So in part B, the cylinder is removed from the hot water bath, and it's able to re-reach equilibrium with the room that it's in. It's essentially brought back to normal. And the lock is removed and the piston is free to move. Does the piston move up or down or remain stationary? Well, if the whole situation is brought back to its initial state, and we're not given any clues about the orientation of the cylinder, whether there are weights on top of the cylinder, whether the lid has mass, maybe its own weight is going to move it up or down. All we know is that it's back in its original state, back in its original internal energy, its original values of PV and T. So the piston stays where you put it, stays where it started. In part C, the piston is pushed in very slowly. And it's pushed in so slowly that the gas inside of the piston is able to remain in thermal equilibrium. And then it's pulled out very rapidly in part D, so rapidly that the temperature of the gas inside goes down. So those are the 2 processes, C and D, sketched on this graph. College Board was looking here that you sketched a concave up curve for C and a concave up curve for D that was below your curve for C. And then we left you with a ranking task question to rank the marked states from greatest internal energy to lowest internal energy. And I know we said yesterday that internal energy is related to temperature. So take a look at those 4 points, A, B, C, and D. But I don't know that we said yesterday exactly how it's related to temperature. So on your screen right now, you see that the internal energy of a gas, U, is 3/2 nRT, or 3/2 P times V, meaning that U is proportional to temperature, or that U is proportional to PV. So knowing this, you may want to grab a screenshot. Knowing this, now we can go back and approach this. If U is proportional to P times V, we can look at the spots on this graph that have the highest value of P times V. Well, locations C and D have a PV value of 20 POVO. At point C, the pressure is 4 P naught and the volume is 5 V naught. And at point D, the PV value is the same. At point A, the PV value is 5 P naught V naught. And at point B, it's only 4 P naught V naught. So point C and D are tied for the highest internal energy. Point A has the second highest, and point B has the lowest internal energy. All right, so you see a process here where a gas proceeds from state X to Y to Z and back. There's process XY, process YZ, and process ZX, which is isothermal. In which process is no work done? So based on yesterday's lesson, we know that work is pressure times change in volume. In which process doesn't the volume change? Well, volume is along the x-axis. So any process with no change in its x value is a process in which no work is done. So process Y to Z, no work is done. And you can see in the text just under the graph that this is a graph of an ideal gas contained in a cylinder with a movable piston of area A. If the area of the piston is A, what force is exerted on the piston during process X, Y? Remember, as a smart AP Physics student, you have to be able to translate between different topics. On the AP Physics 2 exam, traditionally across the 4 questions of the AP Physics 2 exam, we cover a broad spectrum of topics. Now, through only 2 questions, we have to address as much as we can out of 5 topics. So it's quite likely that you're going to encounter a question that relates your knowledge of thermodynamics and maybe knowledge that you associate with fluids. So force is pressure times area. And from this graph, I see that the pressure in process XY is always equal to P1. So the force is P1 times the area.
Okay, and this is what you need to know from today's lesson. The first topic that we'll discuss is temperature distributions, and you being able to interpret a graph showing speeds of the different particles.
Yeah, my apologies, that should say graph, that was on me.
I'm sorry?
That it should have said graph, you read it correctly, I missed the word.
Oh, so we actually showed one last lesson, so we're gonna go just a little bit more in depth about those. Entropy, basically just knowing that explaining macroscopic events in terms of entropy, we're going to talk about some examples in which entropy is increasing or decreasing or neither. And you need to be able to predict the final properties of a combination of gases.
So yesterday, we had this question on screen. 1 mole of ideal gas occupies this volume at this pressure. And then there were several thermodynamic processes through which the gas was brought in a heat engine. And there were a series of questions. First, could you draw this on a PV diagram? Could you find the temperature at each vertex? Could you find the work done on each leg of the cycle? And finally, could you calculate the change in the internal energy on each leg of the cycle? We sort of bumped up against the time wall yesterday, and I wanted to make sure that we did this question justice. So there were 4 states, and the transitions between them were outlined. At first, and then the second leg, the third leg, and the fourth leg. So if you have a shape like this drawn, you're in a really good spot. Now, obviously on the AP Physics 2 exam that you'll be taking, you won't have to create a PV diagram. You won't have to draw any diagrams at all. However, you're going to have to interpret diagrams to give meanings to a figure. So how would you find the temperature at each vertex in this cycle? Well, from the ideal gas law, we know that T equals PV over NR. And we have all the values of PV, N, and R. So I'm hoping that you calculated the following temperatures at the vertices of this process. Notice that the highest temperature is the one with the highest PV value. All right, were you able to find the work done by the gas on each leg of the cycle? Work is P delta V. So along that first leg, there is no delta V, so no work is done. Along the next leg, it's 1800 joules, then another no work is done. It's an isovolumetric process. And then negative 600 joules of work is done by the gas, or the world squeezes on the gas and compresses it. I'm hoping you're able to find the change in the internal energy of the gas, knowing that U is 3/2 nRT, or that the change in U is 3/2 nR delta T. Well, we know delta T, we know N, and we know R, so calculating the change in the internal energy of the gas gets us those answers. We could push this further and ask you to calculate the amount of heat absorbed or discharged by the gas at every leg in the cycle. You'd compare the change in internal energy to the amount of work done. We didn't do that. Thought it was one step too far, but those are the things that you should be able to do for describing heat engine on a PV diagram.
Okay, so we've already gone over the first law of thermodynamics, which was delta U is Q plus W. And today we need to start discussing the idea of entropy in the second law of thermodynamics. And the second law describes changes in entropy for reversible and irreversible processes. We'll define those 2 terms in just a few moments. Now, entropy, just like pressure, volume, number of moles, and temperature, describes a gas at a particular state. Entropy is not how it got there, it's just a descriptor at each individual state. Now, entropy can be described as a measure of disorder or disorderedness, and we'll touch on that later also. The entropy of a closed system never decreases. It can only increase or stay the same. And the total entropy of the universe is always increasing. So think about what's happening to the orderedness of the universe. What's the universe doing? The universe is expanding. It's becoming less and less ordered. Not only is it expanding, we know that we're moving away from distant objects. And not only are we moving away from them, we are accelerating away from them, which is kind of a freaky thing to think about. But that's one take-home message that we want you to know before you leave, that the total entropy of the entire universe is always increasing. So how does that look in terms of different types of processes? So we have reversible and irreversible processes, and we'll start talking about reversible. In reversible processes, the entropy of that system did not increase. So think in terms of, just to kind of put this in a nutshell from physics 1 type terms, if you had a perfectly elastic collision between two objects, you can kind of think about that as a reversible process. Now, if you were to take that situation of something happening and took a video of it, if you played that video in reverse, if it still makes sense and seems plausible that that situation could have still happened in reverse, then we typically can label that as a reversible process. Now, in terms of thermodynamics, we know that there's usually a big picture and a really small picture. For reversible processes, we are strictly looking at the microscopic motions of particles inside of a system. And most of the time, those interactions are reversible. So at the bottom of your screen, you see two gas molecules. Let's just assume that they're the exact same molecule, and they're moving towards each other at the exact same speed. You'll notice that they're offset, and when they collide, what's going to happen? You know from collisions that they're not just going to bounce directly backwards, they're going to take a different path. Now, once those take a different path, if they're still traveling with the same amount of speed, because it can't be velocity, if they're traveling with the same speed, we consider that reversible. And let's talk about irreversible. So basically the complete opposite. Irreversible is when the entropy of the system, the disorder of the system has increased. Now, if you watched a video of an irreversible process that you took, it would look different and does not make any sense if played in reverse. I'll show you a couple of examples in just a moment. But with irreversible processes, we typically think about more of a macroscopic scale of motions. And the example that I have here is a car crash, and we label that as an irreversible process. So I've got a couple of questions for you, a couple of situations, and see if you can label those reversible or irreversible. Now, I'm not going to lie, I think you could argue me all day long about some of them if looked at a different aspect, looked from a different aspect, could be reversible or irreversible. So if you took a hot cup of coffee and you left it on a table in a cool room, and after a long period of time, the coffee and the room reached thermal equilibrium, would you say that that's reversible or irreversible? So here's a question. Can the coffee spontaneously go back to its original hot temperature? And the answer is no. And think about the motion of the particles inside of the room. Are they moving faster? Are they moving slower? On average, I think they're moving faster. So the entropy has increased in this case, and if entropy is increased, we call that irreversible. Here's another one for you. Let's say you just picked up some groceries, or maybe you wanted to make a little bit of breakfast, and you set an egg on a counter and it rolls off the counter and falls on the floor. We all know that it breaks and just kind of splatters all over the floor. So in this situation, again, can you spontaneously, would you ever see an egg spontaneously reassemble itself and go back up onto the counter? Play that video in reverse of the egg falling and cracking. Reverse, uncracking and unfalling back up onto the counter. Is that possible? I don't think it's possible. So we label this one irreversible.
Yeah, we tried this lab in my class once. I had half the class, they took eggs and dropped them, and in every case, the egg broke. And then the other half of the class took broken eggs, like yolky, disgusting messes, and dropped them, and none of them reassembled into eggs.
Shockingly, right? So if you kicked a football and the football follows a parabolic path through the air, would this be reversible or irreversible? And again, if you kind of zoom back out on this and you think about it in terms of a video, if you played it backwards, is it fairly plausible? Does a ball just hop up off the ground, follow a parabolic shape, and travel right back to your foot? I don't think so. I would label this one irreversible. And what about a skydiver parachuting? They're moving downwards at a constant speed through the air, and the air is at rest. Do you think it's reversible or irreversible? Do you think the entropy is increasing or decreasing? I would label this one irreversible, probably. The next one, I think, is a home run. If you had two cars colliding, if you played that video in reverse, so the cars are all crumpled up, if you played that in reverse and the cars just spontaneously went apart from each other and they're perfectly back in shape and look like they just got driven off of a car lot, that's not possible. So irreversible for a car crash.
Alrighty. So one quick follow-up from yesterday before we delve further into entropy. There are two thermodynamic processes that involve changes from an initial state to a final state. Process A and process B. Of these two, which one has a greater change in its internal energy? Which one, process A or B, shows a greater change in internal energy? Well, internal energy is just related to temperature, and both states are at the same temperature, so their change in internal energy is the same. Likewise, you might be asked to rank the changes in temperature for several processes. These two processes would start at the same temperature and end at the same temperature. What if you were asked to compare the work done by the gas for both processes? Which one shows more work being done by the gas? Which one has more area under its curve? Well, that's definitely A, more area between the A, the blue line, and the x-axis. What about the heat exchanged for both processes? Well, if both processes begin and end at the same temperature, they have the same change in internal energy. That energy must have come from somewhere. The energy to do the work must have come from somewhere. If process A did a whole bunch of work while its internal energy changed that much, then definitely process A is being fed more heat than process B. And now, this is an example from a while ago. It's a question that we probably should have asked. If you cool a gas at constant volume, we see that relationship between pressure and temperature that we've looked at before, that linear relationship. But what would happen if you repeated this experiment at half the volume? Same number of moles of gas, same selection, same initial temperature, same final temperature. What if you performed this experiment again at half the volume? Which of those curves would you graph? Would it be curve A? Would it be B? Or would it be C at half the volume? If this were done again at the same temperature with the same number of moles of gas, but instead this whole process occurred at half the volume, which of those relationships would it be? Well, the ideal gas law says PV equals nRT. And if N is not changing, T is not changing, reducing the volume increases the pressure. So half the volume means double the pressure. Last set of review questions for PV diagrams. You asked for it, here they are. Let's talk about the change in the internal energy during some processes. If the internal energy in the bottom left process is just U, what is the internal energy of the vertex at the end of this process, at the end of this isochoric process? The pressure seems to triple, going from 1 atmosphere to 3 atmospheres. So what happens to the internal energy of the gas? Well, if the pressure triples, the temperature triples, and if the temperature triples, the internal energy triples. And what happens along the next leg in the process, the next isobaric process, as the volume increases isobarically by a factor of 2? The volume goes it increases by a factor of 2, so the temperature increases by a factor of 2. But what's the change in internal energy for the whole cycle? If it starts with an internal energy of U and ends with an internal energy of U, there is no change in internal energy. That's the definition of a cycle. Okay, let's talk about the work done by each process, the work done by the gas in each process. Along this top process, this isobaric expansion, the gas is doing work. It's lifting something. It's pushing. It's making a motor turn. It's doing something. Along the next step, that compression, the work done by the gas is negative, or the work done on the gas, we might say, is positive. And finally, in that last leg, the work done is 0 because the gas neither is expanding nor is it contracting. But in the whole process, how much total work was done? Well, the work done, during an entire cycle, the work done is the area of that shaded region. Now, before we continue, I'd like to take a moment to show you how entropy plays out in an ideal gas. So I'm going to switch over to a simulation of gas in a closed container. So on your screen, you should see a closed container, this square thing right in the middle of the screen. And into that closed container, I can inject some particles of gas. And what you'll notice at first, before I do it, I want to draw your attention to something over here on the left-hand side. You can see my mouse hovering, is a square window. It's going to show a number of particles on the y-axis and their speed on the x-axis. It's going to be a distribution, how many particles are going that particular speed. At first, when I pump those particles in, they'll all be going approximately the same speed. But you'll notice here, I have collisions turned on in this simulation. As those gas particles collide, and their speed distributions are governed by the laws of probability, you'll notice that the distribution is not going to be spiked at one central speed. So watch the speed distribution and watch the average speed. The average speed won't change by much, but the distribution of speeds will change. All right, here comes some gas. So you can notice over here, we started with a big spike, and now you already see a spread of speeds, and it comes to about 1,200 meters per second. And even though the average is about 1,200 meters per second, every particle in the gas is going its own unique speed. Now, it's really hard to follow any one particle, but if we could just step right through it, step by step by step by step by step, you would notice that for any one particle, its speed changes with every single collision. But the average speed stays about the same, which means that the temperature stays about the same. Now, I'm going to turn off the speed graph for just a moment. I want you just to watch what happens to temperature and watch what happens to average speed. As we heat the gas, you'll notice that the average speed increases, as does the temperature. If we cool the gas, the average speed decreases, as does the temperature. I'm going to bring it back to about where it was before. We are pretty close, pretty close. So we're going to open up that speed graph again. Now, I'm going to cool the gas. And I want you very specifically to pay attention to one feature. If we cool the gas, we know that the average speed is going to decrease. I'm going to turn that off. If we cool the gas, what I'd like you to watch is the width of this distribution. This distribution of speeds on the left shows how far from the average speed the average particle is. And right now, particles are going all kinds of speeds. Some of them are going pretty slow and some of them are going really fast. And yeah, the bulk of them are going the average speed, but there's some spread there. And I do want to warn you, in this simulation, as I cool the gas down, the graph tends to zoom out, so the peak will look lower, even though it's actually a higher peak. That's my one issue with this simulation. So as we cool the gas, you'll notice that the distribution, the spread, the variety of speeds that these particles can move is very reduced. Now we're almost bringing this down to absolute zero. And on the left here, you see that the majority of speeds now only subtend this small band in the x-axis. Before, we had a wide variety of speeds. We had a very high randomness, a very high amount of disorder in the momentum of any of these particles. But right now, this is a very ordered system. Most of them are going about the average speed. If I heat this back up, watch the amount of spread in the x-axis, the standard deviation, if you're used to that term from statistics, or just the width of the spike. And notice that that spike is flattening out more. The particles are moving a wider variety of speeds. And as the temperature increases, you can see that most of the particles are going pretty far from the average speed. And yeah, the average speed is about 1900 meters per second, maybe 1850. But there's a huge spread in those speeds. All right, in this other experiment, we have on the left side of your screen, you see some heavy particles of blue gas here. They're not moving very fast. They have a highish mass and a wideish radius. On the right side, we see 100 particles with a smaller mass and a smaller radius. I'm trying to hover my mouse over each of those things. The particles on the right have a higher temperature. They're moving faster. And even though they're lighter, their speed is higher. These markers on the bottom show the center of mass of the gas particles with the corresponding color. So on the left side of your screen, you see that the center of mass of the blue particles is roughly in the middle of the blue gas, and the center of mass of the red particles is roughly in the middle. If I open up this data window here, we see 100 blue particles are on the left side and 100 red particles are on the right side. That the average temperature of the red particles is 500 Kelvin, and the average temperature of the blue particles is 200 Kelvin. Now I'm going to remove this divider and some things I want you to keep an eye on. On the bottom, you'll see arrows showing the flow of particles, both leftwards and rightwards. When blue particles move to the right, it'll make the blue right arrow bigger. When blue particles move left, it'll make the left blue arrow bigger. Same with the red arrows. Also, you'll see these sliders for the center of mass move over time. All right, I'm going to remove the divider. And immediately you notice that the net movement of particles is into the box where they were not. That the red particles are on average moving left and the blue particles are on average moving right, even though all the particles are moving in both directions. Up here by the data, you'll see that on average the particles are spreading out. And on average, they are now approaching the same temperature. If two gases are left alone long enough, they will approach the same temperature. They will spread out as much as possible. Their center of mass will occupy the mass of gas will evenly occupy the full space, moving the center of mass. And now we see that the particle flow rate is roughly equal for the blue particles and still equalizing for the red particles, that they have reached thermal equilibrium. And that is what increasing entropy means, going from a disordered state to a very ordered state. So this would be considered a very going from an ordered state to a disordered state. This would be considered a very ordered state. But when they're all mixed and random, that's considered a disordered state. Left to its own devices, gas spontaneously on its own without extra input from us, the entropy of a gas increases. All right, I'm going to move us back to the presentation. And there we go.
Here's your guided practice for today. As usual, we will answer 3 questions. The first question, surprisingly, is about entropy. The second is about energy transfer and thermal equilibrium. And the third is about entropy in a closed system. So here comes your first question. All right, you have some ice cubes and you add them to an insulated cup of hot water. As a result, the temperature of the hot water decreases and the ice melts. What statement best explains the change in entropy of the system, which is the combination of water and ice cubes, on a molecular level? So this is that microscopic state that we care about. So right off the bat, we know that we started with something that was more ordered, just like Mr. Mancino showed, with 2 separate chambers of gas. And when they're combined, we knew that the entropy was increased. So if you combine the ice cubes and the water, you should know right off the bat that the entropy of the system should be increasing. So that immediately gets rid of answer choice A and answer choice B. And again, we know you're not getting multiple choice on this year's AP exam, but these are really good things to be able to think about. So I'm left with answer choice C and D. Both of those increase. So let's take a look at C. C says the entropy of the system increases because the energy gained by the ice molecules is greater than the energy lost by the liquid water molecules. I want to remind you that this system is inside of an insulated cup. So if there was a greater energy lost than, a greater energy gained by the ice than the energy lost by the liquid water, that just doesn't make a whole lot of sense. So energy should stay constant inside of your closed system, assuming that it's a closed system. So let's look at answer choice D just to make sure that that's the right one. It says the entropy of the system increases. That's good, because the disorder caused by the change in state from solid to liquid causes more disorder than cooling causes order. So when the liquid water cools, the entropy of the liquid water itself is decreasing ever so slightly, but the entropy is increasing of the ice when it's melting from solid to liquid. So overall, is a net change in entropy. The entropy is increasing of that system. So answer choice D is the best answer in this scenario.
And I want to draw your attention to something brilliant that Mr. Eaton said. Energy is conserved. The heat energy that flows from the water to the ice is the same amount by which the energy of the ice increases. Energy flows from water to ice, and the same amount of energy flows out of the water as flows into the ice. Energy has to be accounted for, but in that process, entropy increases. The water's entropy decreases, and the ice's entropy increases more. So the entropy of the system increases while the energy of the system remains constant.
All right, and here's our second question. So a student designs an experiment with a curved insulated rod of unknown thermally conducting material as shown in the figure. There's some data about the rod itself, and it says that one end of the rod is touching the surface of water kept at 350 Kelvin by a hot plate, and the other end is just touching the surface of a well-insulated block of ice. So this rod is connecting these 2 substances. So once it is, after a short period of time, that rod is removed from the apparatus and it's placed in a warm room until it reaches thermal equilibrium. So in other words, the entire rod itself is the exact same temperature. One end compared to the other, they have the exact same temperature. So the ends are then positioned to touch the ends to an identical rod with a much colder temperature as shown in that middle figure. How is energy transferred between the rods as they approach thermal equilibrium? So throughout this set of lessons that we've done for thermodynamics, we know that we are physically touching two things together. So we know that there's some kind of conduction happening. So the question is asking though, how is energy transferred between the rods as they approach thermal equilibrium? Now we know that the warm rod, the molecules inside of that warm rod are vibrating very quickly, and the molecules inside the cold rod are vibrating slower, not nearly as fast as the warm rod. And on average, the slower molecules in the cold rod begin to vibrate faster because of the energy that it's gaining from the warm rod.
Oh, I apologize. So a
No, it's
closed
okay.
system, a closed system consists of two adjacent chambers containing the same ideal gas. Initially, one is hot and the other is cold. What explains the change in entropy of that system over time? So imagine if in that simulation, both gases contained the same identical blue particles, one at 500 Kelvin and the other at maybe 100 Kelvin. What would happen to the entropy in that system over time? Well, the entropy would increase. The process is irreversible. The process of reaching thermal equilibrium is directional. We expect heat to flow from hot things to cold things. That is the direction of spontaneous energy flow. Heat will never spontaneously flow from one thing at room temperature to another thing initially at room temperature. That doesn't make sense. Just like Mr. Eaton said, if you watched a video of someone with a cup of coffee in a room and you had a thermometer in the room, a thermometer in the coffee, and you watched the video, it would make total sense if the hot coffee gets colder and the room gets a smidgen warmer. That does make sense. But watching that video backwards wouldn't make sense. You couldn't start with room temperature coffee and a room temperature room and have the coffee suddenly get warmer and the room get colder. It just doesn't work that way. So the process of reaching thermal equilibrium is a random, irreversible process in which entropy increases. So we're going to talk about the mixing of two gases. If we mix two gases that are otherwise identical, same molecular mass, same size, we have two samples here. There's one sample represented by that first curve at a lower average speed, and another sample represented by the sort of flatter curve at a much higher average speed. You can tell the average speed because of where on the x-axis that spike is, where the maximum on the x-axis is. When we mix these two gases, will the average speed be closer to point A on the x-axis, point B on the x-axis, or point C on the x-axis? And let me draw your attention to the fact that the y-axis shows the number of molecules going that speed. So when these two gases are mixed, what will the average speed be? Well, I have a lot more molecules going way closer to the speed, to this speed than at this speed. And those interactions are governed by conservation of momentum. And the conservation of momentum is going to tend to slow down the faster particles and speed up the slower particles, but there are just more slower particles. So the average speed of molecules will be a little bit closer to point A than to point C, a little bit to the left of point B. All right, so a quick debrief and summary. The key takeaways for today is that the entropy of the universe is always increasing. Entropy increases in an irreversible process, and that the entropy of closed systems will only increase over time. that the energy, the internal energy of an ideal gas is 3/2 nRT, or 3/2 PV.
And could you answer these questions after today's lesson? So this is something a little bit different. You haven't cleaned your room in quite a long time, which I'm sure some of you are in that exact situation. Is your room in a high state of entropy or a low state of entropy? And what does it cost you to decrease or increase the entropy in your room? And once your room is finally clean and items are where they belong, describe the level of entropy in your room.
You cannot use the inevitable increasing entropy and unavoidable heat death of the universe as an argument for why your room gets to stay a mess. Don't pin that on us. So here's your AP exam practice. Screenshot this for tomorrow. 3 samples of a gas, that's an ideal gas, X, Y, and Z, are prepared. Each sample has the same number of molecules, but they're at different temperatures. And there are how the temperatures compare. Gas X is colder than gas Y. Gas Y is colder than gas Z. I said that precisely backwards. Gas X is the hottest, Y is in the middle, and Z is the coldest. My apologies. The graph below shows the distribution of speeds, but only in sample Y. Can you sketch the distribution of speeds for gases X and Z, where X is definitely hotter than Y and Z is definitely colder than Y, but they all have the same number of molecules? Screenshot that. Second page, there's a reminder about the temperatures. Then the samples are placed in thermal contact. So conduction of heat is allowed to occur, but even though they're in thermal contact, gas can't flow from one box to the other. But they do eventually reach thermal equilibrium with a final temperature that is greater than Ty. In a few sentences, can you describe the changes over time in the average kinetic energy of the molecules in each sample? So talk about sample X, talk about sample Y, talk about sample Z, from the moment they make contact until the moment that they reach thermal equilibrium. And then can you explain how those changes relate to the flow of energy between the pairs of samples that are in contact? So where sample X touches sample Y, the direction of energy flow is this. And that's why the entropy of sample X does this. And then does the net entropy of sample X increase, decrease, or remain the same as a result of reaching equilibrium? Does the net entropy of the system increase, decrease, or remain the same as a result of reaching equilibrium? So that's a 3-pager right there. To be fair, the font size is a little bit big, but I know it's a lot. The expectation is if you're going to be explaining an awful lot of stuff on the AP Physics 2 exam, entropy and energy and their difference would be a really good topic for explaining that you understand physics too. So we wanted to spend a little time talking about this. In the last example, and here's another 2 screenshotter, 2 moles of an ideal gas are enclosed in a cylinder with a movable piston. There's some data about the piston. Can you calculate the force that the gas exerts on the piston and explain why that force happens? Can you calculate the temperature in state B and explain what temperature means? Can you explain why the internal energy of the gas as it goes from state A to state B, why does that internal energy change as the process progresses that way? And can you determine the change in the total kinetic energy of the gas atoms as the gas is taken from state C back to state A? So take screenshots of those for tomorrow. Finally, before we leave, happy birthday to Mr. Eaton. Today is his birthday. Of course, happy birthday to you, and happy birthday to all the other April birthdays out there who aren't getting a chance to celebrate right now. Next year, we'll all make it up to you, and we'll celebrate double hard if you have missed your birthday this year. So as always, thank you so much for joining us. It's been a blast teaching you about thermodynamics. Moving on, we'll be talking about electrostatics and then circuits and then magnetism. But tomorrow, we're going to start by going over those questions that we left you with today.
Thank you for joining us, guys. We'll see you tomorrow.